So if we were dealing with a problem sine to the m, cosine to the n, where m and n are the power of these functions, and one of them would be odd. If it is odd, it means that we can separate. For example, if cosine, the power of cosine is odd, we can always write it such that cosine dx will be appear here, and the other terms are the power perfect square product things, right? Then if we do so, and we do substitution, we define u to be sine x here, then derivative of u will give us, therefore du will be cosine dx, right? Then we can make our problems, we can write everything in terms of u. Okay. How about if the power of sine is an odd number? Then we can do the similar things. We can rewrite it so that sine x dx will appear here, and do the same things, substitution. But in this situation, we define, okay, u will be cosine x, right? The reason is that when we take derivative, du, it will be, what is it? Yes, negative sine x dx. Very good. So that you see sine x dx appear here, but remember, this has a negative sign. So be careful. So it's better to write it as negative du equals sine x dx. So we can do substitution and we write everything in terms of u. That's it. So, okay. Oh, let's see. And it is very useful to use the half angles identities here. You can look back the table I gave it to you yesterday, or here, sine square will be 1/2 of 1 minus cosine 2x, and cosine square will be 1/2 of 1 plus cosine 2x. But here, now that, or this one, sine x cosine x will be 1/2 of sine 2x. But be careful, when we use this formula, the angle is double. Okay? As we can see here yesterday, suppose, let us continue with the last one, right? I suppose that you have done it at home, but let us do it together and double check it, okay? This guy, let us call it as m, integral from 0 to pi of cosine 2x dx. If you know the general and you do it many times, you will see that is not difficult, but let us just do it as substitution rule and make it easier. 2x, right? The angle here is 2x. If we define u to be 2x, what is the relation between du and dx? Yes, du will be 2 times dx, right? We take derivative both sides. Very good. So it means we can write dx as du over 2, right? What else do we need to do for this problem? Yes, the limits here, right? The lower bound, upper bound. So since we change the variable. So at x is equal to 0, we need to find the corresponding value of u. And what is it? Yeah, we just replace the value of x here. How about at x is equal to pi? Yes, 2 times pi. It will be 2 pi. Okay? Therefore, we can rewrite the formula m is, the integral here becomes integral we write in terms of u. So let us write dx will be, yes, here, right? And cosine of 2x becomes, very good. Now the limit will be from, thank you. Okay, this is a constant, so we can take it out. Integral from 0 to 2 pi. Now use the formula, right? The table. What is antiderivative of cosine? Yes, negative sine u, right? But in front of that, there is a number 1/2. And this is the definite integral. So we need to refine that u is equal to 0 to u is equal to 2 pi. Okay. We replace the upper limit. And here it will be, yes. Oh, because, oh, sorry. Thank you. Okay, good catch. So derivative of sine give us cosine, yeah. Okay, thank you. Uh, so David, right? Alex, I'm sorry. Thank you, Alex. Good catch. Okay, yeah, oh, got mistake. So replace the value here, it will be 1/2 of sine of, yes, and subtract. Very good. Sine of 2 pi, what is it? Yeah, they're both 0, right? Because this is definite integral, we can evaluate the value of at u by specific numbers here, or we can write everything in terms of x, the original variable. For example, we can continue writing this guy here. It will be 1/2 sine, and u will be 2x, right? 2x. And now, because we rewrite it in terms of x, so the limit, we need to use the original limit here from, yeah. Right, so be careful with this. And in the end, we'll still have the same result. Okay? Because, okay, do you have any question? Everything is clear, right? Very good. So let us continue. How about this guy? The hint here, right? Now we deal with something tangent and secant. And remember, we have the relation that secant square is equal to 1 plus tangent square. So it's similar to the relation between sine square and cosine square, right? The sum of them, yeah. So now, so it means that we will somehow substitute a function by one of these two. And let us define u is equal to 10x. Okay, and see what happens. We expect the similar things with sine and cosine. So if we write u is 10x, what is du over dx? Very good. You can use the formula, right? 10 is sine over cosine, derivative of a fraction, and write it out clearly, you see this. Therefore, du will be secant square x dx, okay? So it means that we need to replace secant square x dx by something in terms of tan, right? But original problem is here. It is integral of tan to the 6th x secant to the 4th x dx. What should we do now? Louder, please. Perfect. So here, the 10 to the 6, we just leave it here. Secant square here, a secant to the 4th is secant square, and then square, right? And we know that secant square is 1 plus 10 square, okay? So now everything is good. We can write everything in terms of 10. So what is it here? Yes, very good. But before doing that, because writing 10 is always longer than writing u, right? Let us replace the variable now, and it will save a little more time. So if we thank you, corner. Yes, perfect. That's smart. So it's no longer square. We just yeah, because when I write it, I just keep writing it here this way. But it's always better if we write secant square times secant square here, right? And we leave it this way. And secant square x dx, we can replace it by du. And the other terms, we will write it here in terms of u, here in terms of u, right? Thank you, Corner. It's a good catch. Yeah, when you write. Okay, so if we write it in terms of u, this will be very good. Thank you. And here, this one is du. So now it becomes a lot simpler, right? What should we do? Let us distribute it first, right? This is a product. It looks complicated. So if we distribute it, It will be du, sorry. Okay, be careful. Du. Okay, now things is a lot easier. It will be antiderivative of u to the 6. Thank you. Very good. Continue. Plus 1 over 9 u to the 9. Thank you, Walid. Is it enough? Yes, thank you. And C would be a real number. Can we stop here? No, you're right. So we need to continue, and we write everything in terms of x. It will be right. Thank you. Yeah, right. Thank you. Okay. Do you have any question up to this point? Du, this is a notation. This is simply a notation implying that we need to take the antiderivative of the things inside here. That's it. Just any integral formula we will have, it will be written in this forms: integral of fx dx from a to b, for example. A, b are the bounds, the limits, okay? Or from interval a from b, and x here imply that the variable inside here is the one, the function. The other terms will be constant, yes.
So is that one of the secants squared x gone away? You're doing it in terms of u as opposed to terms of x?
Yes, it's gone away because we here, at this point, we replace secant square by du, right? Substitution. Okay. Quincy and Jonathan, right? Okay. Is there any more questions?
How is the 10 to 6x the same thing as u to the 3?
Because we define u to be 10. Yeah, we defined it. So we make our life easier by doing it this way. Yeah. Anything else? Very good. So, so for trig with tan and secant, it's similar to sines and cosine. So, but the relation is a little bit different here. Secant square equal 1 plus tan square, and you can take a look at the notes I gave you already. So the same trick. If we have to compute integral of tan to the m secant to the n, and n is a an even number, then we can always rewrite it in this form. And in that case, we define u to be 10. Or if here, if you have it here, the other way around, we define u to be secant. And we take derivative of secant. What do we have? Wait a minute a second, here. Secant x, tan x, dx, right?
subbing in secant x instead of secant and
Yes, this guy will be replaced by du, right?
that's for odd power.
Yes, if 10 is an odd number, the power of this is an odd number, then we take 1/10 from this to write it here, and 1 terms of secant, we write it here, right? Because we define u to be secant, so we don't care about the secant orders here, just one order lower, right? And everything here, we can write it in terms of secant. And yeah, okay. Memorize these tricks and we'll be fine. Okay, let us continue. Sometimes, let us compute this integral, secant here. Back in high school, I did not study this formula. I do not study secant. I have no idea what it was. Because secant is simply 1 over cosine. If you remember sine, cosine in relation, tangent, you will always recover all the formulas related to secant. But studying this give us more knowledge and do it faster. So if you want to compute integral of secant dx here, you can always do the same things, compute integral of 1 over cosine x, but it will be a little bit harder. You do substitution, it would be a long page. I did it before, very long. But here, the book teaches a smarter way to compute this integral. And from now on, if we go through these, you can apply this formula. Okay? Let us do it together. Suppose we want to compute this guy. And the trick is that we multiplied this integrand by a number 1. Nothing's changed, right? The number 1, we can write it in terms of secant x plus 10 divided by the same amount. So even, right? Fair. But now, this is the whole number multiplied with a fraction. Then it will be this number multiplied with the numerator, right? We distribute it, and secant times secants here give us, yes, and the next term will be this guy, right? So, and now they define a very smart way. U will be secant square, secant x plus 10x. So we define a new variable in terms of a function in terms of x. So therefore, du will be, we take derivative both sides, right? The left-hand side is du over dx. So we multiply both sides with dx, and finally, and derivative of secant square plus 10x, you do it slowly. So derivative of secant give us secant times 10, right? Derivative of 10 give us secant squared. Okay. Okay, let us get together. Okay, now we take derivative both sides. And the properties of differentiation properties tell us that derivative of a sum will be the sum of derivative. Right? We know that secant is 1 over cosine, right? And 10 is, what is it? Very good. Thank you. Derivative. And from the table, remember, u over v derivative, it will be, what is it? Thank you. U prime v minus uv prime. Okay. Apply this formula to compute the derivative of each of them. This guy, u is 1, v is cosine, right? So u prime is 1 prime, which gives us 0. V is cosine here, right? Minus here, it would be prime. The denominator is squared, right? That is the first term. The second term, compute the derivative of this guy. Oh, do you have a? Oh, okay, sorry. Then the second terms, the same things. Let us square the denominator first, okay? And then the numerator will be the first guy's derivative times cosine plus sine x cosine prime, right? Okay? Just apply the formula. And you can find the formula in the notes I gave you, the table, or go to Moodle's and download it, or review the section part 1. Okay, this guy becomes, oh yeah, thank you, minus here. Thank you, Alu, good catch. So, the first guy here is 0, this is -1, and here, derivative of cosine will give us minus sign, and the minus with the minus here give us plus sign, very good. And here, cosine square, right? Okay. Yes. And here, this guy, sine's derivative give us cosine times cosine, it will be, yes. And the second guy will be negative sine times negative sine here give us plus sine, right? Plus sine squared. Okay. The product here, we can always write the fraction because we can always write it as cosine squared, we write it cosine times cosine. Is that okay? Here, this guy, cosine squared plus sine squared, what is it? Yes, thank you. Very good. Cosine squared here, okay? So, in the denominator, it is a product. So we can break it, we can separate it into two terms. Suppose the numerator, there's a number 1 here. We can always write it as sine x divided by cosine x times 1 over cosine, right? Same here. 1 is equal to 1 square. Something square divided by something square, it will be 1 over cosine x here, and they all square. Okay. So the first guy, what is it? Thank you. And the second guy? Very good. And this guy? Very good. Thank you. So we just review the differentiation rule of a fraction quotient, right? Quotient rule. And from now on, you can memorize it and apply it, do it fast. You want to double check it, redo it, master your skills. Okay. Anyway, so we have this. U prime, which is du over dx, will be 10x secant x plus secant square x here. So this is x. We multiply both sides by dx, therefore we have du will be 10x secant x plus secant x, secant square x here, dx. Okay. Now, because it is already written in the notes, we can just continue here. Okay. So if we define that way, then the whole thing's here times x, right? We can rewrite it as du. Let me write it down. Integral of 10x secant x plus secant square x this is 10 secant plus 10, right? So the whole thing's here. We can replace it by du, right? The denominator, we redefine it and it is u. Okay. Now it becomes integral of 1 over u, and yeah, you can always write it this way. It is always, yeah, this is du over u, or we can write it 1 over u du. And what is the antiderivative of 1 over u? Remember, we are computing in terms of u, right? Here, plus a number c, where c is in R. You can look back at the table to find this simple formula, okay? But is that enough? We need to compute in terms of x, right? The result should be. Therefore, we replace u by the original terms. It will be remember, this is the absolute sign. Okay. So from now on, you can use this formula in the test. Okay. It's a little long, but this trick is very helpful. Do you have any question? Clear, right? Great. So similarly, you can use this formula. Think it's better if I leave it here for you to double check it yourself. Okay? Or you can write it 10. Let us do it together. 10, we can always write it as, thank you. Then we define u will be if we define u to be cosine, right? We do substitution, we will get this result. Okay, very good. And sometimes you need to use, if you see sine mx times cosine nx, or this terms, or this term, use this formula to write a product of sine cosine becomes a sum of different angles. Okay? It's very useful. So let us do some more practice problems here. Suppose we want to compute example 4. The hint is here, right? And this is the integral tan cube dx here. So what do you think about it? Substitution and change to sine and cosine. If we change to sine and cosine, it will be sine cube x here divided by cosine cube x dx. Yeah, it is a fraction. It's not a product as we normally see, right? So this way may be a little more difficult. Anything else? Okay, let us try. So if we write it as 10 square x times 10x here, right? Let us see. Okay, what do we have? Then 10 square, we may be able to write it as this guy, right? Let us just expand it. Okay, it will be secant square minus 1 times 10x here, dx, right? Okay, if we do so, what should we do next? Yeah, just thank you. What is your name again? Amber, thank you, Amber. So we distribute it in one. So when we distribute it, it will be secant square x 10x, right? So it will be secant square x 10x minus 10x dx, right? The first guy looks similar to the strategy we just done. The second guy, we just done it right in front of here, right here, right? So the integral rules tell us that the integral of a difference will be the difference of the integral here. Okay, let us call it I1, and this is I2. And we know from this previous formula here, it is natural log of absolute secant x here, right? Leave it here. And how about this guy? Again, please. Okay, let us define u to be the 10. Then du will be derivative of 10x times dx, right? Derivative of 10x will be secant square, right? Dx. So therefore, I1 becomes, what is it? Right. Okay. And what is antiderivative of u du? Yes, it is 1/2 u squared plus a number, right? Where c is in R. So we're computing this in terms of x. Let us write everything in terms of x. It is 1/2 of 10x squared plus c, where c is in R. Okay, we found I1. Okay, therefore, the original problems will be I1 minus I2, right? Therefore, integral of 10 cubed x here dx will be 1/2 10 square x here plus natural log absolute value of sine x secant x here plus a number, because we use the notation c here already, so let us use a different constant d, and d is also in R, right? So, oh, minus, yeah, this is minus, thank you. Okay. Okay. So, do you have any questions? Oh, we just, yeah, we don't have to. Because here, the first integral, it should add a constant, right? And another constant is from this guy, but in the end, the sum of two constants will be a constant. We just want to avoid using the same notation for different things. You can reduce C if you want, but as long as we understand the difference between these, we're good. So, anything else? So we're good for today. If you have any more questions, I'll still here answer you. I'm sorry, I cannot hear you clearly. Yeah, you should write it C is in R, or you write it as C should be a constant, something like that. Because it is a new thing we should define, so we make it clear. Thank you.
I have a question. Sure. Where did I go? This one? If you do.
Here, antiderivative, the number 7. I think, no. First, there's nothing wrong, but you can always write this in the bracket. This is number 7, right? 7 x squared natural log x. Yes. If we write it in front of this, we just compute here, and we don't have to write number 7 many times. Okay. Avoid writing it multiple times. But here is correct. And here, antiderivative, no. Octet derivative, yes. Then we multiply this guy with this guy. Subtract 1 over x, 7 over 3. Yes. 7 x squared. From here, this is correct, and this guy, oh, you see, this is the power of this is squared. antiderivative of this, it will be cube, right? Divided by 3. And it means that this guy becomes 7 x cubed.
Okay.
Thank you. Yes.
Hey, are you having an office hours today?
Yes, I had it in the morning.